In this segment, we're going to talk about the second law limits on cycle performance, and we're going to continue our discussion about determining the highest possible thermal efficiency for a power cycle, or by extension, the highest possible coefficient of performance for a refrigeration or a heat pump cycle. And for this, we're going to introduce the idea of a Carnot power cycle, which is a power cycle that is completely reversible. There's no irreversibilities within it, no friction or anything like that. And this idea can be extended as well to a reversible refrigeration cycle or a heat pump cycle. And just keep in mind that there is no such thing as a completely reversible process. So the cycle that we're about to talk about is completely theoretical. The only reason that we discuss it is because it allows us to model an ideal case scenario, so we know what the best possible scenario we could hope for was, but we're never going to attain it because it's not actually possible, but we know what to aim for. So we know we're never going to get better than that. All right, so here's our power cycle. You got your cycle in the box in the middle, and it's between two reservoirs. You transfer heat from the high temperature reservoir, you convert some of that to work, and you dump some waste heat in that low temperature reservoir. That's it. That's the power cycle. Carnot power cycle, we're going to use a piston cylinder type arrangement to illustrate our point. And it's made up of 4 processes. We're going to walk through each one. So from process 1 to 2, so this is a reversible isothermal expansion, and you'll notice that I'm kind of ignoring that low temperature reservoir right now. So he's not interacting with our system right now, but he's not gone completely. He's going to come back. So my system's going to be interacting with that high temperature reservoir, which is at a temperature that is just a scotch higher than the temperature of my system. Now, because the temperatures are so close together, we're going to approximate the system temperature as approximately the temperature of the thermal reservoir up here. But because it is just a tiny bit hotter, then heat is going to be transferred from the high temperature reservoir to the low temperature reservoir. Now, once again, because that temperature difference is so small, we can approximate that heat transfer as reversible. Because remember, an irreversible heat transfer would be a heat transfer through a finite temperature difference, not a really tiny, infinitesimally small temperature difference. All right, so we've got a reversible heat transfer, and so as we heat that system up, or as we add heat to the system, it expands. Now, as something expands, the temperature wants to go down, but because we're adding heat to it, we're keeping that temperature constant, and so the temperature of the system stays the same. It stays at that temperature TH. Now let's look at state 2 to 3. For state 2 to 3, we add some shielding. We add some heat shielding, some insulation. So we do not allow it to exchange heat with that high temperature reservoir anymore, but we continue to expand it. And as we expand it, because we're not adding heat energy anymore, as it expands, the temperature goes down, and it's going to go down to a temperature of TL, which is the temperature that it's of the low temperature reservoir that it's going to interact with in just a second. All right, so now we take that shielding away. Now we're going to look at state 3 to 4. This is a reversible isothermal compression. So the temperature of our reservoir is really close to the temperature of the system. However, the system is just a tiny bit hotter. So number 1, because the temperatures are so close together, we'll approximate them about the same. But because the temperature of the system is just a tiny bit hotter, then heat flows from hotter to colder out of the system into that reservoir. And as it does that, the system compresses, and as it compresses, well, as you compress a system, the temperature wants to go up, but because we're removing heat, it keeps that temperature even. So the temperature of the system stays the same at that TL. But now, from state 4 to state 1, so we're wrapping up, we're closing the loop. This is the last process in our cycle. From state 4 to 1, we undergo a reversible isothermal compression. So we take that heat shielding back. We no longer allow heat transfer between the thermal reservoir and the system. And so as we compress it, now our temperature goes back up, and it goes back up to the temperature of the high temperature reservoir. So the temperature of our system oscillates between the temperature of the low temperature reservoir and the temperature of the high temperature reservoir. And if we ran that system in reverse, we'd have a Carnot refrigeration or a Carnot heat pump. All right, So just keep in mind, this is a theoretical cycle, and there is no cycle or process that is truly reversible. The only reason that we talk about Carnot cycles or Carnot refrigeration or heat pump cycles is because they allow us to figure out, well, what's the highest possible thermal efficiency that I could have for this power cycle given those two temperatures that I'm operating in between. All right, now there are two conclusions that can be drawn from a Carnot cycle and the Kelvin-Planck statement. Number one, the efficiency of an irreversible heat engine is always less than that of a reversible one. So what that means is just this. The thermal efficiency of a real cycle, one with irreversibilities in it, has to be less than one that has no irreversibilities in it, one that is completely reversible. And you could extend that to the coefficient of performance. The coefficient of performance for a reversible the coefficient of performance for a refrigeration or a heat pump cycle, for a real one, it's always going to be less than that of an ideal one that has no irreversibilities within it. All right, so the second Carnot corollary says that all reversible heat engines operating between the same thermal reservoirs have the same thermal efficiency. So what that tells you is, say you have two heat engines, two power cycles, and the only thing that they have in common are that they're both reversible, number one, and they're operating between those two temperatures, TH and TL. So what that tells you is, well, their thermal efficiency, if the only thing they have in common is those two temperatures, their thermal efficiency must depend on those two temperatures. So it's only a function of those temperatures TL and TH. All right, well, if that's the case, let's go to our equation for the thermal efficiency of a power cycle. So this is just true for any power cycle. It's 1 minus QL over QH. You can go back and review the video on power cycles if you forget that. But since it's a function of TL and TH only, what we're going to do is we're going to replace those Q's with T's. So this was a relationship that was proposed, the simplest relationship that was proposed, and it works. So this little trick about putting your thermal efficiency just in terms of Q's and replacing it with T's, the same thing holds with the coefficient of performance, as we're going to see in a second. So if you want to know the coefficient of performance for a reversible refrigerator or a heat pump cycle, just take the equation for COP, put it just in terms of Q's, and replace those Q's with T's. All right, so one thing that you need to remember is that those T's you need, when you put your temperature in, it's got to be in absolute temperature units. Got to be in Kelvin or degrees Rankine. All right, so now let's put some stuff together. And if you remember absolutely nothing else from this video, these are the things you need to pay attention to. So right now, pay attention. If you combine this all together, and you know that the thermal efficiency of a real cycle is less than that of a reversible one, so a real cycle having irreversibilities, then you get that the thermal efficiency of a real cycle has to be less than 1 minus TL over TH, keeping those temperatures, of course, in absolute temperature units. And the same thing goes for the coefficient of performance for a reversible or a refrigeration cycle or a heat pump cycle. The coefficient of performance for a real refrigeration cycle has to be less than TL over TH minus TL. Coefficient of performance for a heat pump, a real heat pump, has to be less than TH over TH minus TL. So these are just the equations for COP, just putting them in terms of Q's and switching out for the T's. So, all right, so once again, you remember nothing else, remember those three equations, and you'll be good. All right, well, thank you very much for watching, and let me know if you have any questions.